All right, so we are asking now what happens if we stretch. So what happens in general for a self-avoiding polymer? Because here we are still working with ideal polymer. Okay, so in the case of self-avoiding polymer, we see again that when we impose stretching, there is a characteristic length coming out. So we interpret this as a blob. So the relation there remains valid, that there is a characteristic length scale induced by the force, which is given by the thermal energy divided by the force. Energy divided by the force is a length, of course. But what changes is that our blob is not described by the statistics of an ideal polymer, but that of a self-avoiding polymer. Therefore, inside the blob, now we will have G monomers, and the scaling is that psi of B is given by G to the power nu. So for instance, if I redo the same calculation as before, and I would find an F star where I would have an N to the power nu. So you could repeat. So for a self-avoiding walk, if we calculate F star, the minimal force that gives some perturbation to the polymer size, that is given by kBt divided by A n to the power nu. Okay. Now we want to understand what happens when we stretch a self-avoiding walk. Okay. And then we can use this blob theory to that case. Okay. So we know that in general, for any model, self-avoiding or polymer, for small, so what we are looking at here, stretching a self-avoiding walk, a self-avoiding polymer. Okay, so a real polymer where there is self-avoidance. Okay, so we know in general that when we stretch a polymer, there is a regime, always a linear regime. Okay, given by this entropic elasticity, we discussed this. So we know that K, the constant, the spring constant, is given by kBt divided by radius square of the polymer when F is equal to 0. There is a factor 1/3 and so on, but not so relevant. This is kBt. And for a self-avoiding polymer, this is n to the power 2 nu a squared. Okay, right. So this is the first regime. Okay, so until when is this first regime lasting? Exactly up to valid F is of the order of F star. And if we replace F star here, we see that the X corresponding to F star is exactly, if we do the math, we see that, okay, that we get an X star, which is of the order of n to the power nu, sorry, A times n to the power nu. Okay, so for small forces, up to this force F star, we are not significantly perturbing, and we see that the distance between the two endpoints is within the radius of the polymer. Okay, so our self-avoiding walk up to an F star has the two end distance remain confined within the radius A n to the power nu. Okay. Then we have another regime. Because when we start stretching more, then we have blobs appearing into the system. So if higher forces, so for forces F larger than F star, we have blobs appearing. Okay, we have one blob, another blob. I draw them a little bit quickly here. Okay, and more and more. Okay, every blob has a size psi b. So what is the end distance, the n distance scales typically as how many blobs I have, so the number of blobs times the size of each blob. Okay, so I have nb of this blob. So nb is the number of blob, and it is given by the total number of monomers divided by how many monomers I have in each blob times the size of the blob. So G I have it here. So G is given by xi b divided by A to the power 1 over nu. So if I now multiply this by A and divide it by A and divided by A such that I have psi b over A, then I get from here psi b over A to the power. So I have 1 from the first term, okay, and I have from G, I have a power, I solve for G, I replace it with psi b over nu. So if you do the math, you find 1 minus 1 divided by nu, all right, which I can also write as n over A. Then I have kBt divided by Fa to the power 1 minus 1 over nu. Okay, so this is putting all the things together. If you remember, this nu is smaller than 1, is the Fourier exponent. It's between 1/2 and 1, smaller than 1. So this means that this is in total, it's a negative power, so I can reverse it and write it perhaps more in a better form. So I can write this one here. Say there is still a bit of space, so I write it here. Psi scales as NA, and then I write FA divided by kBt. Right, and I change the sign of this power. I get 1 over nu minus 1. Sorry, 1 over nu minus 1. Okay. So, you know, for 3D self-avoiding polymer, nu is the Fourier exponent, is equal to 3 over 5, right? Okay, so I have 5 over 3 minus 1. Okay, so I find 5 over 3 minus 1 for 3D polymer. Fx scales as F. 5 over 3 minus 1 is 2/3. Okay, so if I replace the ideal polymer, which is 1/2, this is 2 minus 1 is 1. Is x still linear with the force, also in this regime, okay? But for self-avoiding polymer, I see that there is now a second regime. So therefore, I can summarize the result here. So this is the prediction of the blob theory, is that we have a new scaling law. So what we find is that if we plot extension as a function of the force, often we plot the other way around for force as a function of the extension. If we plot extension as a function of the force, we get the following scenario, and we plot in the log scale, because we have power laws here. Okay, at small forces, this is linear, so there is a power 1. Okay, so here, x, the first regime, x scales linearly with the force up to a certain force, which is of the order of f star, log of f star, and from here on, there is power 1, and there is the power which we have calculated is 2/3. So here x scales as, sorry, is off scale. We do it again. So this is one law, this is the other law. X scales as f to the 2/3. here on this other regime. So this is what our blob theory predicts for this force extension. There is a change of regime and a crossover point.